Hey, section 2.5, complex zeros in the fundamental theorem of algebra.
Fundamental meaning the basic reason algebra exists in the first place.
Something like that. So that's our first theorem that we're going to look at in this section out of two major theorems. And it actually, as far as theorems go, is pretty straightforward. It says a polynomial function of degree n has n complex zeros, real and non-real. Some of these zeros may be repeated.
So basically, if you've got a fourth degree polynomial, you have 4 zeros, except some of them might be imaginary, kind of like Mrs. Stevenson's friends.
Right. No, not like. Okay, anyway, before we talked about that, it has at most that many zeros because we were only talking about real, but now we're going to start talking about like imaginary.
Imaginary.
So if it's a degree of something, that's how many zeros it has, real and non-real included.
Sounds good.
Yeah, the linear factorization theorem is the next theorem, and it just basically is a continuation of, we've seen this earlier, that if we have certain zeros, we can write them as linear factors like this, where we have x minus a 0, and all that. And
it's the whole synthetic division stuff that we were doing in previous sections where you had to divide all the way down and have the statement x minus 5 times x minus 3 times x minus 2.
Right. And again, we've looked at the polynomial stuff with just real zeros, but now when we're talking about complex zeros, all of these things are still true, even if we're talking about complex numbers instead of real numbers.
And complex numbers are just going to be those numbers that have I in them somewhere. Which,
yeah, and we're going to talk about that
in all actuality, that's every number. But we're going to really dive deep.
In a second.
We're going to dive deep.
Okay.
Couple rules about complex numbers?
Well, more like just some things to remember. And you kind of started to say this on the first one. All numbers are complex, like all of them are, because standard form for a complex number is a plus bi, where a and b are numbers. But
what if b is 0?
What if b is 0? Exactly. So that's a situation where, like, we could write the number 5 as a complex number because
I agree.
Because it's 5 plus 0i.
So when I get out my phone and I call somebody, I'm actually punching in
complex numbers.
Complex numbers.
Absolutely. All of them are complex numbers.
Busy.
Yeah, of course. Speaking of imaginary friends. Anyway, yeah. Number 2, remember that the square root of -1 we can write as I. I know before now we have been like, oh, let's not even worry about those imaginary numbers. Now we're going to start worrying about them. And then in
a safe, professional way.
Yes, and then an I squared is -1. So those are things that we're going to use when we're simplifying and whatnot.
The tricky one actually is going to be the I squared. As a student of math, most of you are pretty good with the square root of -1 being I, but that whole I squared thing sometimes can be a little tricky. So just commit that to memory in there with song lyrics.
Yeah, so if what happens is we'll get something when we're simplifying like 4i squared, and then you don't want to leave it like that because I squared is really -1. And so 4 times -1 gives you -4. So that's like a simplification process that's really pretty easy that you just have to go through. And so once you get used to it, you can probably skip from 4i squared all the way over to -4.
Yeah.
So example 1 here, we're going to do a lot of multiplying in this section. We want to write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. Before we multiply it out to put it in standard form, can we go ahead and do the zeros and the x-intercepts?
I mean, we could. We sure could.
Our zeros are anywhere that these 3 parentheses where those equal 0. So we probably don't even need to write it out, but it'd be like where x minus 1 equals 0, x minus square root of 2, I equals 0, and so on.
X plus the square root of 2i equals 0. Look, I got the last one.
Yeah, good job. And that means that x equals 1. That's not what I was trying to spell at all. I was trying to say zeros. That was bad. My bad. Zeros. Our zeros are
x equals 1.
Okay.
X equals square root of 2i. And that's an imaginary number.
Yes.
And x equals negative square root of 2i, which is also an imaginary number.
Okay.
It's an irrational imaginary number.
Yeah, so it's got double duty i's right there. Now x-intercepts.
The x-intercepts are all the places where this graph crosses the x-axis, which happen to be the real part of this.
Yeah, so any real zero crosses the x-axis, any imaginary one doesn't. That's why it's an imaginary zero, because you can't actually see it on the graph.
Right, it's invisible.
So our x-intercept would be at x equals
Right, x equals 1.
Okay, now we're going to multiply this out, and so you always want to start with the ones that are paired together. Like I would not distribute x minus 1 through first. I would do this right here and FOIL this.
That's a great start to this problem, and the reason is you can actually shortcut this because we're going to use one of the rules about multiplying binomials that says if you have two numbers that are identical and then you have a plus sign and a minus sign inside your binomial, there's no middle term, which is what we want. We don't want any square root of 2i's running around. That'll just foul things up later.
Right, so good old FOIL. If we have, this is called the sum and difference of
squares.
Yeah, sum and difference of squares. And so if this is happening where there's signs are the only thing that's different, your outer and inner terms cancel out. So instead of doing FOIL, we just need to do FLA.
Full. I love a good full.
Anyway, so first is x times x, which is
squared.
X squared. And then these can be tricky until you get used to them. We're trying to do negative square root of 2i times positive square root of 2i.
Square root of 2 times the square root of 2 is 2.
Yes, and a negative times a positive is negative.
So minus 2i squared.
But wait, isn't I squared something?
I think I squared is, negative 1.
Negative 1.
I almost went to Google, but then I remembered.
So really, instead of having an I squared there, we can just change it to a plus 2 instead. Gotta make sure I don't erase it.
Get the inker.
Okay, and so what happened over here was we got negative 2i squared, and then we changed it.
Negative 2
positive
times,
2.
yeah, negative 2 times negative 1.
Yeah. Now we can FOIL this out.
And he's not so bad.
No.
This is one that you should be able to FOIL in your sleep, I think, because you've seen it a ton of times. Right?
Maybe not in your sleep, but still it should come pretty readily. X times x squared is x cubed. I want these to go in order, so now negative 1 times x squared is negative x squared. X times 2 is 2x. And negative 1 times 2 is negative 2.
Negative 2. That's what I said.
That's what you said. So that's right there as our answer.
You got it.
As well as what we did earlier with the zeros and the x-intercept.
So that takes care of everything for this particular graph.
Yep.
Lot going on.
Yep.
Conjugate zeros. These are actually one of the more awesome things about dealing with complex numbers, because I know that a conjugate is going to actually undo itself at the end. Right.
And so what's happening in this little blue box is that if we have a polynomial with real coefficients, which is all we're really going to deal with, that if I know that a plus bi is a 0, then I also know that a minus bi is a 0. Those have to end up being together every single time.
Which means that you have pairs of complex numbers when you're looking for zeros. So if they give you just one,
you know there has to be another one.
There's just one more.
Yeah. So for example 2 here, we're writing a polynomial function of minimum degree in standard form with real coefficients whose zeros are negative 3, 3 minus i, and 2 plus 5i. And the tricky thing here is those aren't really the only zeros.
No, there's 2 zeros they left unsaid, which would be the conjugates of 3 minus i, 3 plus i.
And a conjugate just means you write the same thing but with a different sign in front of your I.
Only in the middle. Precalculus mistake number 17 is to make everything negative.
Yeah, that's just silly.
And that's not going to work. You only change the middle sign. That's it.
Yeah. So if we now want to go through and actually figure out what this polynomial would be, we have this real 0, which is negative 3, so that's x plus 3. And then whenever we do this, we do x minus 3 minus i. And then we have x plus, no, just kidding.
X minus.
No.
This is 2, so it's x minus.
Yeah. No, sorry. X minus 3 plus i. I got caught up in the negatives.
The whole negative positive
and
things.
Then
keep going. No, there's more. There's more. Yes.
Minus
there they are.
2 plus 5i. And x minus 2 minus 5i. So we've got our work cut out for us here.
Quite a bit of work, actually.
Okay.
But if you work with your conjugate pairs,
it'll be a lot easier.
It will be easier and doable.
Yeah, so let's start off with the 3 minus i and the 3 plus i. Distribute. Would you say distribute?
Distribute is a great idea.
Okay.
I love distributing. I have distributed the handwriting to you.
Delegated would be a better word there, or
And
something.
I think we'll both agree your handwriting's better.
Yes, we will. And so will everyone in the audience, I'm sure.
So notice those end parts are opposites. That means that we shouldn't wind up with the middle term.
Right. So what we're going to do is use our skills of foiling. And so when we FOIL here, we always do x times x, which is x squared. Our outer and inner terms are always going to be added together.
Right.
So we need to think about this and say, what is -3 plus I plus -3 minus I? If I add those together, what do I get?
-6.
Right. And it doesn't completely cancel out, just the i's cancel out, which is great. Because then we don't end up with an imaginary number.
We really don't want any i's running around at all when we get done with this.
No, we don't. And so that gives us our middle term, and there's always an x with our middle term. And then our last will be -3 plus I times -3 minus I. So now we're multiplying the two numbers together. Well, I kind of wrote that backwards, but they're
Plus
both
I
there.
minus I, they're
Yeah.
both there.
Okay, so we, again, only have to do first and last on this because these are the same thing with different signs in the middle. So -3 times -3.
So you're going to have 9 minus I squared.
And
But wait,
there's more.
there's more. If you act now, minus I squared becomes +1. Yes, indeed.
Yep.
So we're dealing with a 10.
Yes. So that's our last number over here is a +10. So that's these two that we started off with multiplied together. And the more you do it, the faster
easier
it
it'll get.
becomes. So that's one of our polynomials.
Go.
Okay, so now x minus 2
Minus 5i.
X minus 2 plus 5i.
Right. And we're going to follow the exact same pattern that we took on the bottom, on the part that we did in green down here. We're going to go ahead and square that first term, x squared. And then when we look at that middle term, you know, where we have -3 plus I, -3 minus I, and we put those together, we're doing the same thing now except with -2 minus 5I plus -2 plus 5I. Well, -2 plus -2 is -4.
Right.
So
and the i's
-4x.
cancel.
And the i's cancel.
So that's -4x.
Right, right.
Now if we multiply together -2 minus 5i times -2 plus 5i, we're going to get -2 times -2, which is 4.
Right.
And then -5i times 5i is
Minus 25i squared. Okay, but again, there's more. If you act now.
you'll get that I squared to change the sign right there.
That is correct. That is correct.
that
So we're
equals
actually
29.
29.
Okay.
So there's part number 2.
And so what we have to do is now come back and see what all we've got over here. We've got f of x equals.
We may need to wipe this slide clean to finish.
Yeah, we may need to. Then we have x squared minus 6x plus 10. And then x squared
Minus 4x
minus
plus
4x
29.
plus 29.
It's going to be really long. Now, one thing that we can get from this, we know we're closing in on the end because when I look at this problem that we just wrote down now, I know I'm going to have a fifth degree polynomial. And I know that that's going to be my minimum degree.
Yeah, because we've got 3 zeros. Can I just like drag this up?
Yeah, highlight it. And pull it up. Pull it up. Bum, bum.
We don't want to run out of room.
No, we need
Middle of
room. There's
explanation.
gonna be a lot. Pick
What
your
would I-
pencil.
Yeah, pencil. Okay.
Okay. So now, pick your poison on this one. You're gonna have to foil. It's just gonna get nasty.
well,
And-
we can't even foil. We're basically distributing.
Yeah, we're distributing, and it might be easier on this to actually do the whole vertical multiplication and adding of like terms.
Do I need to write that down then vertically, or do I just?
Well, write it like it's got. So let's just go with x squared times x squared.
Okay.
So let's just.
Are we going to distribute this x?
Yeah,
right there?
and then we'll write it across the top there.
Okay.
We'll leave the x plus 3 to the end.
Okay. So x squared times x squared is x to the fourth. X squared times.
Minus 4x cubed.
So minus 4x cubed.
Plus 29x squared. And then next row down.
So now we're doing the negative 6x.
Negative 6. So that's going to be negative 6x times x squared is negative 6x cubed. And notice how we're going to line everything up now as we go. So that way it'll be a little bit easier to see everything. and you're not all strung out all over God's green earth with numbers. So
negative 6 times 29.
6 times 29, not one we carry in the old back pocket, 174. And then the last row, 10 times x squared is 10x squared. Erase that other 10. And then, you know, what is that? Minus 40x plus 290.
Whoa.
Wow, that's big. And then put all that together. You might even need to pause at home while you add this up and count fingers.
Yeah. And toes.
29, 24, and 10. 29 plus
63?
24 plus 10. 63. She's a math goddess right here.
I like to keep, you know, lots of numbers in my head.
And you didn't count on your toes.
No,
Impressive.
no, I didn't. But that's not all.
Wait, there's more. For the price of nothing at all, you get to distribute the last little bit. And again, it might be easier to do, again, a vertical style, just because there's a lot going on.
Yeah, just because there's a lot going on.
Quite a bit.
So distribute the x through.
X to the 5th now, which is where we're going to end up finally, a 5th degree.
About time.
About time indeed. Quite a lot.
Now, I don't know if you've looked ahead at what we assigned from this section, but I'm pretty confident that this is longer than any of the problems that
This is quite a great example. It is truly a beast.
Yeah. But if you guys are worried, I don't think it'll be this bad when you do it yourself. Hopefully, we're getting to a tricky spot
63
here.
times 3, got it. 189.
642.
642, 90. Sorry,
next
290 times 3. I'm on it. It's 870.
Can you do 3 times 214?
3 times 214. Got it. 642.
What's 3 times 290?
870.
Okay. And then vertically add. Okay, finish this problem up by just adding like terms. So,
hey, guess what? Your like terms are stacked up neatly already.
Yep. So x to the 5th doesn't have a like term. Here we've got negative 7, x to the 4th. 63 minus 30, that's 33. X to the 3rd.
Negative 2.
I think that if you turn it on.
On is good.
It's right there. Negative 25.
Negative 25. X squared. I'm on that one.
And then 290 minus 642. Positive 290.
Okay, so 290 minus 642. 352 on the negative side of things.
And then 870 is its own term. Hey, look, we did it.
All done. Yay! Now, on something like this, it's going to take some patience, some practice, and you've got to be organized, or you're going to just
completely get lost, screw something up.
Yeah.
So.
And notice how careful we were to line everything up. This
Yeah.
is a better strategy. This is a pretty good strategy for handling some of these longer problems.
Yep, definitely.
All right, good talk. Okay, we've got a graph here of this function x to the 5th minus 3x cubed plus 6x squared minus 28x plus 24. We want to write it with a linear factors, which means lines.
All factored out.
And we want to find all the zeros. Now, real quick, the fundamental theorem of algebra tells us that we were going to have 5 zeros.
Because it's a 5th degree polynomial.
Yeah, and that means 5 complex zeros.
Right.
So
now, if we look at the graph, I can see
1, 2, 3.
Okay, and we can even maybe like label those because it looks like this one.
That's going to be right there at negative 3. Yep, and 1, and possibly, quite possibly 2.
Okay, and what we can do, because we can't see the other ones, they are obviously imaginary, is we can use synthetic division to whittle down this polynomial basically until we're left with something where we can find the imaginary
synthetic
zeros.
division comes back.
Yes, it's like the best thing ever. So
It really is, and I know it looks weird and you don't like it, but it's really an outstanding way to do stuff.
yes,
honestly.
much better than long division, that's for sure. Make sure that you remember there's a 0x to the 4th that we need to take care of here.
Which will get you, this is pre-calc mistake number 75.
Yeah, definitely.
Mm-hmm.
Okay, so we do synthetic division here, and since we think it's a 0, we should end up with a remainder of 0. So we just knock this out real quick.
If you don't get 0, double check your math and then double check where you crossed the graph.
Yeah, because you may have looked at it wrong.
You may have looked at it wrong. You can always use your rational roots theorem as well. So you got some options.
That's an 8.
Positive 8. Look at there. Negative 24. 0. Boom. Shakalaka. Chitty chitty.
Yeah.
Bang bang.
Yeah. So now we started with an x to the 5th. So if we did decide to rewrite this would be x to the 4th.
For Rizzle.
So just kind of keep that in mind. But now we're going to do synthetic division again. Let's use
1.
Yeah.
I vote 1.
We can use whichever one we want to.
1.
But let's use 1.
Let's use 1.
And when we do this, we're not going to worry about that 0 there.
No
okay?
zeros, no synthetic division.
Yeah. So do it again.
Chitty chitty bang bang. Walla
I don't know
walla.
why you keep saying that.
Walla walla bing bang.
It's not like we're changing signs or something.
Dang it. Looky there.
We got a 0.
It's party time.
Now, we can go one of two ways here because we are now at x cubed here. And it looks to me like we could factor this by grouping.
But don't do it. No.
Okay.
Synthetic division way easier than grouping. Honestly, we've got another 0. We know where it is. So
yeah, don't worry about that 0. 1, 2, 0.
Oh, even better. I already like how this is lining out. Look at that. X squared plus 4. That is glorious.
So let's solve this by subtracting 4.
Let's do.
From both sides.
Righto.
X squared equals negative 4.
Yep.
Square root.
Yeah, and remember, when you take the square root of both sides algebraically, you get plus or minus the square root of something.
Yeah, so let's talk about what this is the square root of. Square root of 4, I know what that is.
The big deuce.
Yeah, it's 2, and the square root of a negative number means
I.
So this is plus or minus 2i.
There we go.
So it asked us to do two things. It said find all of the zeros.
Which we have now done.
Yeah.
Negative 3, 1, 2, and plus or minus 2i. Those are all our zeros.
Right, and so here they are down here. There's all the zeros. It also asks us, though, to write f of x in its linear factorization.
So that means that we're going to break this up now into its little individual components and put them in long style.
And we just use our zeros for this. So x plus 3, x minus 1, x minus 2, and then even our imaginary ones, these aren't so bad.
They're not bad at all.
Plus 2i.
X minus 2i.
Yeah, and it doesn't matter which order you put those in because we know we're always going to get these in pairs. Remember, those imaginary numbers are always going to come in pairs. So if you had accidentally forgot the plus or minus, remember you have to put them in pairs. Otherwise, this wouldn't. When you multiply it out, it wouldn't work out right.
Wouldn't work.
So that's the other part of our answer.
Finito.
Example 4. It tells us the complex number z equals 1 minus 2i is the 0 of this polynomial. Find the remaining zeros, f of x, and write it in its linear factorization.
Z is almost always going to refer to an imaginary number.
Yeah, instead of seeing x equals, a lot of times we see z because it's a complex number.
Not a zombie.
No, not because it's a zombie. Because zombies aren't imaginary. They're
real.
Yeah, okay. We, just like if they had told us like that 4 was a 0 and we'd use synthetic division and then find the rest of the zeros, we can do the same thing with 1 minus 2i. We can use synthetic division.
So 1 minus 2i, you can actually do synthetic division with this. Even though it's a complex number, it's still a thing that you can do synthetic division with. And don't forget, there's an x cubed that's missing.
Yeah.
So
put a lot of space here because when we start multiplying this, we're going to need it.
Gonna need the space. It really is a space eater. But you treat it just like any regular 0. You treat it the same way you would as if it was a 5 or a 2 or something.
Right. So we drop down the 4, and then we're doing 1 minus 2i times 4, which you distribute
4 minus 8i.
Yeah. And then you add 0 plus 4 minus 8i, which is 4 minus 8i.
Now, a really kind of a cool trick you can use is you can actually do imaginary stuff on your calculator. So when you're doing synthetic division, it kind of helps a little bit with this.
Yeah. Go to mode and make sure you're in
A plus BI form.
Right. It's about 6 or 7 down.
It's close to the bottom.
It says A plus BI instead of real.
And the I sign is right above the period. So you would hit the second key and then the period to bring it up. So.
Then put them in parentheses and go to town on multiplying.
Yeah, so I forgot the parentheses. Did you just take a bite of sandwich?
No.
What, are you getting ready to eat a chip? I'm working here. I can't believe that is unacceptable that you would do something like that. So the answer for this is going to be negative 12 minus 16i, and we're just going to add 17 to it. Well, you can only add 17 with 12. You can't put 17 with the I part. So we get this guy. Oh gosh, there's more. So 1 minus 2i. Dang it, I forgot parentheses again.
You could just press enter
Shucks.
and then multiply.
1 minus 2i times 5 minus 16i. Negative 27 minus 26i. The i's have it.
Okay, so we add 14. We added 14. Now we're timesing again by 1 minus 2i.
Parent-teacher conferences tonight, sorry.
Yeah, sorry. We're in a kind of a time crunch here. Minus 65. Oh, look, it's 0. Hooray. Now, we need to do it with another 0.
The conjugate of 1 minus 2i. I know what that is.
Okay, so remember, we're not going to worry about that. We're going to do 1 plus 2i.
All you have to do for a conjugate is change the middle term, or the middle sign.
Yeah, so here we go again. But this time it will work out better because look, the conjugate. Oh, so this is 8.
Oh, geez, no wonder that didn't work out. I'm telling you. And now, this is a great example. This is a great this is a great example of how to find a mistake when you're synthetic division. The reason we know we had a mistake was because when we got done synthetic dividing, we knew we weren't going to get a remainder of 0. But we knew that 1 minus 2i was a 0.
Yeah.
So we know that 1 plus 2i has to be a 0, and we didn't get that. And since we didn't get that, we know there's a mistake. So we have to take a little second, take a bite of food, and look, and we found that 4 plus 4 is 8, not 0. Bam! Now we're off and running, and look what happens. It really is a 0. Case closed.
So, since we started with a 4th degree polynomial, we did synthetic division twice. We're at 4x squared plus 8x plus 13 equals 0. We could try to slide and divide this.
Quadratic formula.
Okay, I'm okay with that because if it is factorable, we'll find out pretty easily here. 8 squared is 64.
These things also tend to have a tendency to not be factorable.
That's unfortunate.
Which
I love
is,
factoring.
I do too. Factoring is really nice and pretty, but these don't always work themselves out that way.
64 minus 16 times 13.
Negative 144. Code imaginary.
So that's 12i?
12i. The eyes have it.
You've already used that joke once.
Dang it.
Okay, and if you're simplifying this, you have to be able to divide everything by it. So we can divide everything by 4. So that'd be negative 2 plus or minus 3i
over 2.
Over 2. So everything gets divided by 4. You can't just like simplify half of it and not the other half.
And I would say leave your answer right. This is a good answer.
Yeah, I like that answer.
There's no need to split it up into 1 plus or minus whatever, because what if you don't whatever it correctly? So stop right there while you're ahead. If you keep going and you make a mistake simplifying, now instead of getting the problem correct, you get the problem incorrect, and we don't want that.
Yeah, so we had 1 plus or minus 2i that we started off with knowing, and now we know this, and so the factorization of this, we're going to have, how do we want to do this? X
minus, 1 plus 2i.
Okay.
Yeah, that's the only way to do it.
I wasn't sure if we wanted to distribute.
You can if you want to. You can always distribute, make it pretty, but I mean, I'm good with this. What do you think? I mean, well, here's the distributed part.
Oh wait. Oh, yeah. I just started distributing, didn't I?
You did. It's okay. Let them see some distribution.
No, we don't need to.
All right. I agree.
Okay. All we have to do is put x minus, and then put in parentheses here, negative 2 plus 3i
over 2.
Over 2.
Leave it how we found it.
And then I ran out of room, but x minus negative 2 minus 3i over 2.
Over 2.
And the book does something weird on these. If you look in the back of the book, which would just be silly, does something weird. So if
it does do weird. There's no need to do the way the book answers.
No, definitely not.
Hey, so we're going to look at writing this big old fancy thing out with linear and irreducible quadratic factors. And irreducible what?
That means you can't reduce it into linear quadratic factors.
Ah, just like on the previous problem where we had to use the quadratic formula and it didn't work out so perfect.
Right. So I graphed it on the calculator.
The time is 4:30. Parents are arriving. Please check your way down to gym conference area.
There you go. Now you know when we recorded this lesson because we're not taking time to re-edit.
Yeah.
So
We're in a crunch. There is 3 minutes left.
or less.
Do synthetic division. -3 is
Negative
0.
8, 24, 0, 0, negative 8, 24,
All right.
-3. What's going on around here?
Let's see. +3 is also a 0.
And we can use +3 with the numbers that we just discovered. By the way, don't have to do that last guy. Now, while Mrs. Stevenson's working this out, I'm just going to tell you that we've taken our equation from a 5th degree polynomial down to 4th. As Mrs. Stevenson is wrapping up this part, we're going to go from a 4th degree down to a 3rd.
Now, there is another 0 on here, but it's a fraction, so I'm afraid we're going to have to factor by grouping unless we just really want to try to guess it. No, okay, I'm right. I was like, wait, what? I guess we could find the 0, but I've already got this written down.
Okay, go for it. Go for it.
I can take out an x squared and be left with 3x plus 1. I think it's going to be -1/3.
I think you're right.
And then out of this, I would not take
It's going to be
anything.
-1/3.
So it's 3x plus 1. And then to finish that off, we have 3x plus 1 times x squared plus 1. And so
there it is. There's
Yeah.
the answer, actually. And by grouping.
Well,
which
but
is
we
what
need these
talked
first
about.
two as well.
Right.
3x plus 1, x squared plus 1, and then x plus 3 and x minus 3.
And the x squared plus 1 is your irreducible quadratic. We could use quadratic formula on that to find the imaginary number, but in this case, they don't want us to.
Yeah, they didn't ask us for the zeros. They just want us to write it as a linear factorization. So we take the zeros we used up here, and then this right here, because I can't split x squared plus 1. It's not x plus 1 times x plus 1.
No, it is not. And
It's
don't
not.
write that. That's pre-calc mistake number 12.
Yeah, that's ridiculous.
Yeah,
Don't do that.
Don't do
If it
that.
was x squared minus 1, we'd be good,
Mm-hmm.
but not x squared plus 1.
That is correct.